Let find out that you're able to see my screen. I'm ready to jump right in.
Go for it. I see it.
All right, fantastic. Actually did skip my bio slide since Kevin did a wonderful job introducing me. So since we do have a lot of content, I'm just gonna jump right in with our objectives for today. Um, First of all, we're talking about Cosmos DB, and this is somewhat of an advanced session, but I'm still not making any hard assumptions that you are familiar with Cosmos DB. So we will at least review the most basic concepts, the most fundamental concepts in Cosmos DB that you'll need to understand in order to follow along with the rest of the session, and namely partitioning. Then we'll talk about the change feed, what it is, what it can do for us, and how it works in Cosmos DB. And then we'll kind of tie those two together to build microservices. So we'll apply the concepts of partitioning and our understanding of the change feed in order to build several real-world event-driven microservices today. So let's start by talking about the change feed. And we have in Cosmos DB what's called a container. This is to us as a single logical resource where we read and write documents. But as it turns out, as we deposit documents into the container, though that gets emitted through the change feed and persisted in the change feed, such that you can treat the change feed, let's say, similar to a transaction log in a traditional relational database like SQL Server, for example, where you can just kind of always rewind this thing and play the events back from the beginning of time. And that lights up a number of very interesting possibilities. The first of which is replication. And I'll explain what I mean more by replication. That's a very general term. Cosmos DB itself is geo-replicated, and that's not the type of replication I'm talking about. It also provides redundancy through replication within its data centers, and that's also not what I'm talking about. I'm talking about a case where you might want to copy data yourself, and we'll talk about reasons why you might want to do that and how that can be achieved. If you are not familiar with NoSQL, you know that data modeling, you may not be aware that data modeling in Cosmos DB is quite different than it is in the normalized world of relational databases. And so very often we'll need to denormalize data, and we'll talk about what that means. But that can be done by listening in on the change feed. Obviously, any event of interest can be picked up on the change feed to generate notifications. We can create what are called materialized views, which is essentially a very cheap and inexpensive and lightweight data source to query against compared to the raw underlying data behind that view that would be very expensive to query against. And certainly any data coming into Cosmos DB, you can just pick up on the change feed and ship it downstream. Just move it downstream, and so that could be to any destination. Let's say data lake, blob storage, or SQL Server, perhaps even. So basically, you can achieve all of these by building these event-driven, so-called event-driven microservices. And we're going to go through all of these today, and the first few through slides, and the last several through a nice demo that I've prepared. And what's really nice about this architecture is that each of these microservices that you build for these purposes, they could all tie into the central change feed. There's no interdependency, which is really ideal with microservices, right? I mean, keeping them independent, keeping your microservices independent and not relying on one another, it certainly makes for a much simpler architecture overall than one that does have those interdependencies. Right. So as you'll see through the demos, these microservices can independently consume the change feed. They can independently maintain their own state in terms of where they're up to in the change feed as the events are being emitted. Each one of them could be brought down and brought back up and played back independently of the others, all through this architecture. So let's jump into that first part. Like I was saying, we have to have a discussion about partitioning. It's hard to talk about anything in Cosmos DB without having at least this little brief primer on what is called horizontal partitioning, where again, like I said, you have this container, which to us is a single logical resource where we read and write documents, but behind that container, okay, is in fact what you could call a cluster of servers, if you will. Each of these black boxes being like a machine in the cluster, a server in the cluster. Technically, these are actually what are called physical partitions, which is more than just a machine. It's actually a unit of replication behind the scenes to achieve redundancy within the data centers hosting your Cosmos DB data. However, for the purposes of our discussion, let's just think of them as a box, right? I mean, in the end of the day, the cloud is the cloud, but at the end of the day, stuff's going to land on a box, and that box is going to have CPU and storage. So you can store things in each of these, and each of these has throughput capabilities through a CPU processing in each one. And there's really no upper limit to the number of servers in this cluster. And so theoretically, at least, if you, again, and we'll get into this, partition your data properly, you can achieve both unlimited storage and unlimited throughput, right? Because you just add more physical partitions, each one of which gives you more storage and more throughput. All right. So I talked about physical partitions, but really we have to concern ourselves with what are called logical partitions. So what are these? Well, let's drill in a little here, okay? I've got my set of physical partitions here, and there's 3 of them. And again, documents are going to land on each one, but is it going to be arbitrary? No. In fact, Cosmos DB is going to know where to store each of these individual documents based on the logical partitions. And this is something that we define. So Cosmos DB is in charge of the physical partitions. It automatically adds them and automatically manages them. But we're the ones that are in charge of the so-called logical partitions by defining a partition key on our data. So when you create a new database, that database is going to have a container, and that container, and don't think of that container like a table in a relational database, because as you'll see, you can store many different types of schemas in one container, unlike a table, right? But the hierarchy is the same. One database will have one or more containers, and each container is going to have a partition key. And I'm going to switch to a scenario here of a social networking demo, where for that partition key, I'm going to choose the username property. I'm going to basically say every document's going to have a username property, and that's what I'm partitioning on. And the result of that would be, and if we like actually forget about the physical partitions, which is often helpful to do because we don't have to concern ourselves with those, and just focus on the logical partitions, that would mean that in this social networking scenario with the username as the partition key, that each user's documents will be grouped together in the same logical partition. So all of Tim's documents in one logical partition, all of Andrew's in a separate logical partition, and so on. And again, each of these documents can be of different types. It's not like a relational database where there's an enforced schema. So this could be the single document that exists for Tim's user profile, and the next several could be Tim's posts. He's made several posts, and there's a document for each post. And Tim may also have comments on other posts, and those might be these documents with a different schema yet for comments, and these might be likes. So these are all documents of a different type. They all have different schemas, but the one thing they share in common is the username property that is Tim in this case, right? And that's the idea of logical partitions, right? Using that kind of scenario. But you'll see other kinds of scenarios where you'll start thinking about these logical partitions and how you want them to be organized in order for you to pick the right partition key. So a logical partition will never span physical partitions, that is certain. But which physical partition a logical partition lands on is up to Cosmos DB. So let's talk about some common, let me pause to see if there's any questions to this point.
No questions as of the moment.
Okay, great. Thank you, Kevin. And so let's talk about some common partitioning patterns, all right, that you might find in Cosmos DB. So let's look at these 2 physical partitions. So we are schema-free, meaning you're free to define the schema for any document, but the only one requirement is that every document has a property called ID. You have to have an ID property. And that ID property is not unique across the entire container. It's only unique within a logical partition. So in fact, that means if I partition on the ID property itself, I'm only going to get one document per logical partition. And this might seem like an odd pattern, right? Because it means that if you can't have more than one document in a single logical partition, then if you need to query across documents, like in the social networking example, to get all of Tim's posts or all of Tim's likes, that would not be efficient because they'd be not all contained in a single logical partition. But depending on your scenario, if you are dealing with single document like a key value store, where you need to use Cosmos DB as a super performant, highly scalable key value store, where you need to read and write documents by their IDs. IoT scenarios are a very good example of this, especially when ingesting data. You could partition on the device ID, but there could be issues with that when you start gathering too much telemetry data for one device. But as you'll see in this presentation, we're going to balance this across other solutions that are going to allow us to query on this data. So let's just say for an IoT scenario where you need to massively ingest a massive amount of data at an extremely rapid rate. Like in our scenario, the demo I'm going to show you, with airplanes that are emitting telemetry data, every 10 milliseconds, if you will, and you need to capture each one of those documents. Actually, this is a good pattern because you are going to get the most uniform distribution. Cosmos DB is going to be able to most efficiently scale out as necessary because there's only one document in each logical partition. Sometimes, this is for big data, but sometimes you need to store data that's not so big in a database, and like inside Cosmos DB. So imagining the IoT telemetry data for an airplane, which would be a gargantuan amount of data. On the other hand, if just your roster of flights that you run as an airline, right? You're an airline and you have a roster of flights that you run. That list of flights is going to fit comfortably in a logical partition, which, by the way, is limited to 20 gigabytes in size. So for any kind of small or reasonable size lookup list that's not going to approach anywhere near 20 gigabytes in size, the pattern very often is to use the type property. When I say the type property, it's a type property that you supply because there's no requirement for any properties other than ID. So you could, and it's anyway good practice to have a type property, because that's beside the point. But you could have a type property and set its value to the same string, in this case flight, in every document, and that's going to group them together. And if you likewise have a list of airports that you service, which is again is a manageable size list, every type property in the airport documents would say airport. And if you were running an e-commerce website and you had a list of product categories, which again is one of these lookup lists, then each type property would say category. And what application doesn't have that list of states and provinces, right? You need that drop down, right? Similarly, each state province document would have a type property of state. This could turn into an hour-long session alone, just going on about what are good candidates for the partition key. And this is not a session on partitioning. So we're going to stop here and just say that in terms of other types of queries, it's going to depend on your scenario. We saw the social networking example, but here's a similar type of example where, you've got, you're going to optimize for your most common queries, where most commonly a customer is going to want to retrieve their information, which includes their orders. The order details are embedded as JSON in each order, but the point is that they are documents of different types. Customers and orders are different types, but because the partition key is the customer ID, they are logically grouped together per customer. And that's where we'll stop on common partitioning patterns. And I'm doing a quick time check, and it seems to be okay. So, I'm pretty much on time considering we started 10 minutes past when we should have. So I'm going to jump on and talk now about order change events. Now, this is really important because I'm going to talk about, it's really all about events, right? So I'm going to use a shopping cart scenario here, for example, where this particular container itself is is storing shopping cart data, but not stateful. It's not like storing a shopping cart document that has all the items in the cart inside of it, a document that you insert and then update and possibly delete, or if you will. But instead, we are just modeling these documents as events. Anytime something happens in the shopping cart, we generate an event. And that means these are only inserts, no updates, no deletes. So for example, the cart's created, an item gets added, another item gets added, the first item gets removed, and so on. So that's not a delete, right? And here at the end, the second item gets modified. Maybe the quantity gets updated on an existing item. That again is not an update. That's an insert. All of these are inserts, because all we're doing is anytime one of these things happens is we're generating a document to Cosmos DB, and that's getting emitted through the change feed. And it's quite obvious that these need to be processed. Anyone that's processing this sequence of events has to process them in order, obviously, because if you add two, if you can't remove an item before it's been added, so they, and so on. And now imagine a set of microservices that are consuming these events, that are watching on the change feed, and each has a purpose. And one of them might be a purpose of generating such a materialized view. I mentioned a materialized view. It could actually build and maintain a stateful view of the entire shopping cart. It could watch these events, and when an item gets removed, it can remove that from that document. But that could be one microservice. There could be another microservices handling fulfillment as events occur, or tax calculation as events occur, and so on. So with that in mind, let's drill down into what's behind the scenes of a container in Cosmos DB. So just like a container is one logical resource for us to interact with, behind which there are actually multiple physical partitions, well, there isn't really. There is one logical change feed that you get on the container, but in fact, there are multiple physical change feeds, one per partition. So if I have two physical partitions behind my container, there are actually two change feeds, one on each of these physical partitions. Now you'll see soon, we don't have to concern ourselves with this. Everything will get aggregated for us, but it's important to understand how order change events occur in the face of scale as partitions expand. So if I partition on the cart ID and the first customer starts their cart, Cosmos DB lands a document for the event of creating the cart on physical partition 1, and there's a logical partition for that entire cart, all the events in that cart. And then that user sits there and stares at an empty cart while another user opens another cart, and that's in separate logical partition for customer B. And it arbitrarily lands on physical partition 2. As far as we're concerned, not arbitrarily, Cosmos DB picks keeps things balanced, so it puts one on one, one on the other. And while the first customer is still staring at the screen, the second customer adds an item to their cart, and third customer comes along, a fourth customer comes along, and so on. Items get added, items get deleted, items get updated, as I was describing. And each time one of these items is being added to the cart, they've been emitted through the change feed in the order that they occurred, right? So on each one of these physical partitions, within the logical partition, the events are emitted and stored in order, right? Cart A's event 1 always precedes cart A's event 2, even though cart C's events are interleaved, okay? But now at some point, well, hopefully at least, because hopefully business is booming and we need more physical partitions to handle more events for more shopping carts. So what's going to happen at some point is that Cosmos DB is going to perform a partition split behind the scenes. And this is seamless and transparent, but it's going to spin up a new physical partition and move roughly half of the logical partitions from the physical partition that is being split over. So, and of course it has its own change feed, naturally. All physical partitions have their own change feed. So it moves this logical partition and actually many others. Like I said, roughly half of the logical partitions get moved over. And when that happens simultaneously, the events that were persisted to that change feed of the partition being split get moved over, preserving their sequence. And so now as things progress and events occur across all three of these physical partitions, what I said before remains true, that if you look at each one of them, within the logical partition, the events are preserved in sequence. And so now, do we have to concern ourselves with 3 change feeds because we have 3 physical partitions? No, of course not. That's why we have powerful SDKs, and we have the change feed processor library, and it's going to basically take, aggregate this all for us. So yeah, there's the point being made that if you scan each one of these down, you're going to get them in order per cart, which is what you need, right? If a microservice is operating on these carts as events occur, that's what they need. They need them to be preserved in that order. So here are the events that have persisted to our 3 physical partitions. But in fact, if you multi-thread across all 3 of these, such that now they're interleaved at the physical partition level, and you have a single logical change feed, you can still see, no matter how they get interleaved, that regardless, you are processing each cart in the order of events that occurred within that cart. It's a core critical concept for being able to implement any of these types of systems. So I'll pause to this point to see if there's questions. And silence is compliance, and therefore I will continue. Can I just get some confirmation that I'm still being heard out there?
Yes, we hear you.
Okay, great. Thank you. So how do we consume the change feed? It turns out there are several ways. This is the least desirable way, and in the early days, this is what you had to do. You had to do what I said, you don't have to do. You have to discover the physical partitions and process each one and do your own multi-thread and do your own scale out, right? And also do your own, manage your own state, because like each microservice has to know the point, its checkpoint, right, where it's up to in the change feed, and that needs to be persisted somewhere. So you have to do all that work, and you don't want to do all that work. There's something called a pull model, which is, I guess, interesting. I mean, when you consume the change feed directly, you are pulling, right? You're discovering the physical partitions, and then you are pulling the events out of the change feed, maintaining your own state for checkpoints. The pull model, but it's undesirable for a number of reasons, as I pointed out. The pull model actually has some nice capabilities. It is scalable, so you don't have to worry about multi-threading, and you don't have to discover individual partitions. You get a single change feed. But you are manually pulling it. You are like you're pulling from it. But the nice thing about it is that there's a single partition key option. So if you're interested, for whatever reason, on consuming the change feed only for a given physical partition, like only for a given tenant, let's say in a multi-tenant scenario where you're partitioning on the tenant ID, then it could be an interesting option. But by far the most common and preferred way is to use the change feed processor library. This is a push model where you sit back and you let the events get pushed to you. It's stateful, it's scalable, it keeps track of the checkpoints in a special container called the lease container that I'll show you in a moment. So you don't have to worry about state, you don't have to worry about scale. As there are more physical partitions, this thing will just scale out, to each of the physical partitions. And then there's Azure Functions, which is really just a serverless wrapper around the change feed processor library, meaning that it's just a very convenient and easy way to take your microservice that you might have implemented to run, not in the cloud or not on Azure, just hosted with the CFP library, easily with a serverless function. Wow. Sounds like a lot, right? So what we're going to do is we're actually going to go through all of the, I'm now going to start going through those various scenarios that we stacked at the beginning. There's replication, denormalization, notifications, materialized views, and data movement. I'm going to go through them one at a time. First few with slides, and then we're going to jump into the live demo. So pause for questions. Cool.
Still no questions.
Okay. All right, so I don't know if that's good or bad, but meanwhile, I'll plow forward talking about replication. So we're talking about this condition that's commonly referred to as analysis paralysis, where you need to choose that partition key. And in many cases, it's an easy choice, but in other cases, perhaps many other cases, it's not always simple. Yes, it'll be based on your most common querying pattern, so that most of your queries can be satisfied by a single logical partition and not have to turn into what's called a cross-partition query, where the query has to fan out to all the physical partitions, which is undesirable, not necessarily evil. Let's say if it's a small percentage of the time, and don't ask me for a number, because it depends on a variety of other factors, but if it's generally the exception rather than the rule, there's nothing wrong with a cross-partition query. But if you're hammering away, like in an IoT scenario, with queries like arrival boards and real-time flight maps that are constantly querying for this information. Though if those queries you do not want them to be cross-partition queries. So you can only choose one partition key. And what happens if you have really more than one? And I don't just mean like a 90% to 10%, I mean like 50-50. Well, what do you do then? You can really run into a problem. So the answer then is replication, where you basically have one container partitioned on one partition key and a microservice that replicates that data over to another container where it's exactly the same data, but it's partitioned on a different property, you see. So let's see what that looks like, why you might want to do that. Let's look at a shopping cart example, and this is now as a stateful shopping cart example, not the stateless version that we were looking at earlier. So it's not event-based, it's just more like a representation of your cart and what's in your cart. And here I've got 2 Surface Pros in my cart. And it's partitioned on the cart ID. So if I want to run any query on a cart, it's going to be efficient. So I need the full cart. That's the query. And the partition key is known. So it's a single partition query. If I don't need the full cart, just a subset of the cart, it's just the same, because I can then say, I can filter that down to only Surface Pros or only items where in the cart where the quantity is greater than 10 or the price is greater than 100, all of that stuff. All of those queries are satisfied this way. But what if I actually need all the Surface Pros across all the carts, right? That's a whole different, ball game where it's not just the occasional time that I need that, but it's like equally it occurs equally with the cart-based queries. I need the item-based queries. Well, the partition key isn't known. That would make it a cross-partition query in the first container. So instead, I'll create a second container called cart by item. And I'll partition that on the item property. And guess what? It's going to have identical data because by listening on the change feed of the cart container, I can just replicate the document over, right? I have an identical copy there. But there, the item property is the partition key, and so I can query on items very efficiently on specific items across all carts. And then, of course, further filter down on all Surface Pros, with a quantity greater than 5, right? That kind of thing, and you would get all the shopping carts where any customer that ordered a Surface more than 5 Surface Pros, you can very efficiently retrieve. So it's actually, there's this cost in the overhead of implementing the microservice and replicating the data over, but that cost is outweighed by the benefits of the that you get when you need to query, since these are both very common querying patterns that run very frequently. So in terms of processing updates and deletes in this scenario, it's important to understand, or in any scenario, but in this scenario, it doesn't impact us. There is this sort of limitation where the interim updates are not retained. So if a single document is updated multiple times, the change feed only retains the most recent change. Now, for our purposes, it's not a problem, because if we ever lose our replica container and need to rebuild it by rewinding the change feed effectively and replaying it, all the events, well, then we only really need the latest version of the document, right? So it's fine. But for other scenarios, it might not be fine. And so that's a consideration, which we'll talk a little bit more about. For deletes, and both of this is like for today, there's a preview, and the preview out there that's supposed to remedy this, but deletes themselves are not written at all to the change feed. So that could be a serious issue if somebody deletes something from the cart, right? Like, so if I change the quantity from 2 to 3 here on the left side, the microservice wakes up and now is updated here on the replica side. Same thing if it gets changed to 4, it's going to get updated to 4 right here when the microservice does that. But what if now we need to delete this item, the cart, like the user deletes the item from the cart? Like I said, if you just delete it from the cart on the left, it will not be written to the change feed. It will not be picked up by the microservice, and you will wind up with an orphaned row, which you obviously do not want. So, like I said, they're working on correcting this, but the remedy for today is to use the time to live capability. This is a feature in Cosmos DB that lets you self-expire documents automatically, which has a variety of use cases. But in this case, we're using it as a bit of a hack. What we're saying is we're not going to delete the document. We're just going to update it, but we're going to put this special property called TTL that Cosmos DB respects, and that's going to trigger the update. And our microservice can be written in a way to see if the type of update is that a TTL property was added, interpret that as a delete, so that the microservice deletes it from the replica container, knowing that Cosmos DB 60 seconds later will delete it from the cart container. So to remedy this, there is a private preview in place for what's called the full fidelity change feed. But the downside is that it's not, does not let you go back to the beginning of time. It is a finite retention period of 30 days maximum, but it captures not just inserts, but all the updates and the deletes. So if your scenario requires it, you will have that option as long as you can live with the 30-day retention. It'll also give you more information than you get today. Today, you can't distinguish between an insert and an update. So all you can do is upsert, if you know what I mean. There's no metadata, but the full fidelity preview will tell you the type, whether it was an insert, update, or delete. It'll give you the previous version. You can do that kind of compare of current values and original values, and whether it's a delete operation through TTL. All right. On to our next application, which is denormalization. So Cosmos DB is non-relational. This comes as a shock to newcomers from strong backgrounds in relational databases, where the concept of no joins and no relational constraints is very, very jarring. So it takes a lot of getting used to. It's a paradigm shift, and it makes you wonder, without rejoins and without relational constraints and being non-relational in that manner, is it even suitable for handling relational workloads? And the answer was, of course, yes. And I have a whole session on that, which we can present in a future date. But the short of it for here is that you just need to think about it differently. You need to use different techniques in order to materialize those relationships that you have between entities. And denormalization is one of the ways in which you do that, where you actually duplicate data. Which is like a cardinal sin in the relational world, where you have one instance of the data, and you have your one version of the master data, and you join on that, and so on, to keep that single instance. But in the case of Cosmos DB, we want to make sure that our queries get satisfied with a single request and don't require multiple requests because there are no joins. And that just and just don't care about the storage, and we'll figure out a way to keep our duplicate data in sync with the master data as it changes, and that way is using the change feed. Smart, right? So here's my product document. It's got a bunch of IDs in it, including a category ID and tag IDs in that array down there. That's a string array of tag IDs, but there's no display information. Like if I have this document and I want to actually display on a web page the full information, including the name of the category and the names of the tags, I can't do that because that data is stored in the product metadata container, a separate container where I've got these lookup lists of categories and tags. So it would require one query to get, let's say, all the documents from a given category, knowing the category ID but not its name, and then another query to get that category name. And then the worst part is, then for each tag in that array, for each document returned by the first query, running this other query, which does check all the items in the array for a match on your tag. But if this sounds painful, and then it is. It's because it is. And if it's there's not a solution that will scale. It'll be very expensive and will cost a lot of processing power, which means a lot of request units that you have to provision, which means a higher Azure bill. You just don't want to do that. So what you actually do instead is you actually store copies of that information, of that master data. Like in addition to the category ID, you include the category name. In addition to the tag ID, so it's not a string array anymore. It's an object array with the ID that we had before and the actual name copied from the master data. So if I have one of these documents in hand, I have everything I need to display it on my web page. But then the question becomes, obviously, how do we keep that duplicate data in sync if the master data changes? What if a category name changes or a tag name changes and you want to propagate that change? So here in this particular example, I've got these tag IDs with these names, and I've got the category ID and I've got the category name is duplicated, like I was mentioning. And here in the product metadata container, I've got master data for categories and tags. And there's a change feed that we can listen to with a microservice that will propagate changes across. So if shorts, for example, the category shorts with an ID of CSH gets changed to fun shorts for whatever reason, that microservice can update all the documents on the right, or we pluralize this tag name outdoor to outdoors, where it's still singular here and it still says shorts here. Well, we can propagate that change out to this document and all the other documents that have those IDs, that have matching IDs. By the way, this code, I have code for all these microservices that come with this session. It's just that I have to, in the interest of time, I can only show demos for the last set, which is coming up very soon. And you're going to see everything you need to know about building these microservices in Visual Studio. So, and we're there, because now that takes us to our next set of microservices, which were notifications, materialized views, and data movement. And for that, we're going to have live demos using the Contoso Airlines IoT scenario. So we are a small airline, but we have great aspirations. We only serve the continent of the US with 12 flights and 6 airports, but we want to grow. And so to accommodate our growth, we're going to choose Cosmos DB. And we have these requirements. Obviously, we need that real-time flight info. We'll need to know where all our planes are as they're up in the air. We need to make sure they're not flying over areas they shouldn't and generate alerts if they do. We need an up-to-date arrivals service in order to, support all our clients that are looking for arrival information and all the arrival boards that you have up at the in the airports. And we need to capture all this telemetry in order to do that. But this is information that whose usefulness in terms of lifetime is very short. Once the plane lands in its history, after 30 days, we don't need to keep this stuff in Cosmos DB. Maybe we can archive that over to cheaper storage like Azure Blob Storage and remove it from Cosmos DB. And these are all of our requirements that we are going to satisfy by creating microservices. You guessed it. After ingesting all that flight telemetry, we'll have microservices that will generate those notifications, those email alerts if you fly into a no-fly zone, create materialized views so that your real-time flight info and your up-to-date arrival board can be very inexpensively retrieved, and will archive to blob storage for permanent archival. All right, so for ingesting flight telemetry, we're going to have a location container, which I'll show you in a moment. It's going to receive all the flight telemetry. It's going to be this huge container, right? Because every 10 milliseconds, our planes are emitting the speed, the altitude, the duration, latitude, longitude, right? Every 10 milliseconds, each flight is doing that. So we're going to partition on the ID property like I showed in the earlier part of the demo. So it's going to be exactly one document per logical partition. This is highly optimized when you're bulk ingesting device telemetry in real time, right? And it needs to just scale infinitely. Like the device ID won't do, because that's going to grow to more than 20 gigabytes at some point easily. All right, so our first microservice is going to track all flights. It's going to constantly monitor each flight's location. When a flight enters into a fly zone, it will trigger an alert, and it will do that by monitoring the change feed, examining each document in real time as the plane is emitting it, and run a spatial query against designated no-fly zones. All right, let's jump right in. So I've got a lot of stuff to show here. we're going to start by having a look at my solution. Hopefully you can see that that pretty clearly.
Yes, we see it very clearly.
Great. Okay, then I'm not going to do that because that causes lots of headaches. All right. So you can see I've got a set of projects here in my Contoso Airlines solution folder. And of them, 4 of them are microservices, as we were discussing. The email alerts, the materialized views for real-time flight location and arrival board, and the data archival microservice. So each one of these 4, and then besides that, I've got a desktop application that is just the eye candy here. A generator, which is the simulator, and that's code I will not be getting into, but it essentially is what's bulk loading our location container, and this shared project. Now the rest of all of them have common code that share. Now all of these 4 microservices projects, these are Azure Functions projects, and you can certainly create a single Azure Functions project and have multiple functions in that one project. But that would violate our principle, right, of independence. So that would create some sort of interdependency in terms of debugging and deploying. Deploying rather, right? Meaning that if I need to redeploy one of them, I need to redeploy all of them. And so it's just better to keep them isolated and have one function per project named after each microservice, which is what I've got here. And another nice thing in that is that in Visual Studio, if you're building these things in Visual Studio, you can run them all concurrently. I am actually running them all concurrently. See, all 4 are up and running. They're all very quiet right now because my flights are all grounded. But as soon as I kick off the generator, you can see them all wake up. They're all going to light up. And there's the email alert. There's the current location for the materialized view. There's the arrivals board for the other materialized view. And there's the data archival for blob storage. Right, they're all ready to. They're all eagerly listening on the change feed, and here's my flight gener. Sorry. Here's the actual flight generator that I'm going to kick off in a moment. When I kick it off in a moment, you're going to see activity, a flurry of activity across all 4 microservices as they independently track events. But what's really nice is that you can, in Visual Studio, in your local environment, run all of these concurrently and debug all of these concurrently. You'll see each one has a local settings JSON inside of which there's a port number. So my email alert microservice is listening on port 7071, but the current location microservice is on 7072, and the arrivals board is on 7073, and the data archival is on, you guessed it, 7074. So I can therefore like run all and debug literally all of them at the same time, which is exactly what I'm doing now. I don't have the debugger attached, but I could. All right, and then the eye candy. Well, this is what you do when you're grounded at home when COVID strikes. So I was like kind of had a lot of free time on my hands in those early dark days of COVID, and I set out and built this this little flight map here, and this is actually Windows Forms. I'm not ashamed to admit. It is using the Bing's map control for WPF, made possible in Windows Forms by the WPF interoperability in WinForms. And here I've got all my airports that you can see that I light up here. These are the 6 airports that I service. These are my 12 flights that are flying in my fleet. And if I check this checkbox here around Washington, D.C., you can see that's our no-fly zone alert. So that's some defined radius around the center of Washington, D.C., where if a plane flies into that area, we need to be notified via an email alert notification. So before I kick this up and start running it, I'm going to first switch on over to the Azure portal and show you our database. This is our location container. It's very, very large because I've pre-populated it in advance. Like I told you, the ID property is the partition key, so that's why we see the same value in 2 columns here. And if you look at each document, you can see that it's got all the information I was kind of describing. Well, there's the type. It's a location document, and there's some static information that is the same for every event. Information about the flight, departure, arrival, how long the flight is usually, and in distance in miles. But then the rest of these properties here are all very dynamic. Latitude and longitude, altitude, speed, the remaining minutes, remaining miles, that's constantly changing. And take note of this important, is complete. This is important because, at least the way I designed the demo, is complete gets set to true once and only once the moment the plane lands. That is an event you do not want to miss, or you will miss the landing of a plane. So we're going to see about the significance of that in a moment. And here's time to live, which is I was mentioning time to live in another context, right? As a hack for dealing with no deletes in the change feed. But in this particular case, this ties into our fourth microservice. Our fourth microservice is going to archive each of these documents, or let's say a subset of these documents, because we don't need to archive each and every one, over to, except we don't want to miss this one if it's true. But otherwise, it doesn't need to be each and every one, over to Azure Blob Storage. And this value here is expressed in seconds, amounts to 30 days. So our data expires out of Cosmos DB in 30 days, but it gets archived on the fly as the planes are flying into Blob Storage. All right. With that, I'm going to flip on over to the code for the email alert microservice before I actually start running it. Oops. So here's our email alert microservice. And everything is in this email alert function, which I'll pump up font size nice and big for you. So there are a bunch of privates that I'll get to in a moment, but let's start with the public entry point, if you will, our email alert function. And this function name attribute is what makes it an Azure function, named email alert. It doesn't have to match this name, although I don't know why you wouldn't want it to. For sanity's sake, keep them the same. This is exposed as email alert as an Azure function. And this function, or method, if you will, has a Cosmos DB trigger attribute in it. And that is a metadata for the Azure function to know how and when to fire. What database are we watching? I'm using a constant, but you can see in the tooltip, it's the Contoso Airlines database. What container collection is the old name for container? Unfortunately, it hasn't changed everywhere. So many places use the word collection, but it's synonymous with container. So the container that we are watching the change feed on is the location container. That's that gargantuan container, which, by the way, I said it was gargantuan, but how big is it? Let's do a select value count. Oops. And there are, 34 million. Oh, or is it 3,496? Yeah, 34 million, right? 961,192. That's quite a few, and actually, it's not really even a lot from a big data perspective, but it's enough to make our point. And it's going to just start growing once our planes take off, once we start the simulator. So that's the container that we're watching. The connection string information is stored in this local settings JSON file. We were looking at it a moment ago. It has the port number, but it's like the equivalent of app settings JSON. This, when you deploy this to Azure, you'll have to get this configuration also deployed as settings for the Azure function. And there's the Cosmos DB connection string that I'm referencing here, so that the Azure function knows, the account name and the endpoint. And the key, rather. The name is the endpoint, and then there's the master key. And then these other values here, you'll see in a moment, are used for actually sending the email. So that's going to be specific from one microservice to the other. I mentioned the lease container. You need to have it. It will, when we have one, and it is right here. But it's not part of our data model, really. So the location container is the big one. The metadata is just stores our small lookup lists, right? Our lists of airports, our lists of flights. That's what's actually driving the front end to know what airports and flights are available. It's coming from the database, but it's very small static data. And remember, we partition on type for those small lookup lists, and we have all our airports are set to airport, all our flights are set to flights. The lease container should be empty. I think it's empty. Yeah. Well, no, it's been left. It's still lingering from my earlier running of the demo. The current location is empty. That's our materialized view that we're going to see soon, and the arrivals board is also empty because our materialized views haven't been created yet. We haven't started our microservices yet. But what's important is that we distinguish each microservice that's sharing the same lease container with a unique prefix in order to avoid collisions and in order to achieve isolation in terms of maintaining checkpoints distinctly from one microservice to the other, because they could all be at different checkpoints, right? Now, all that information is wrapped up in this one large Cosmos DB trigger attribute. In terms of the actual parameters that are passed to your Azure function, it's only these two, which are the only two that you need, right? A read-only list of documents that have changed, and a way to be able to, write to the log. And what we're doing here is we are checking the flight location. We're iterating each one. I'm not going to get into error checking because it's a long topic, but it's extremely important. So it's usually good to have a very top level function that with a single line in the try that does all the work, and a catch that would do more than just log an error. It would preferably just stash it away in a queue to be processed later and not try to really cope with the exception, because you have to be very spry with these microservices, right? They have to operate very quickly. So we're going to call check flight location. We're going to pass in the document that changed. Now here's something that's important, and I told you I would get back to those privates up again at the top. This could be running in parallel across multiple threads as changes are happening very quickly across multiple partitions. And even within a single partition, there's going to be multi-threading happening behind the scenes. So your thread needs to be your code rather needs to be thread safe, and that's where these privates come into play. This one here in particular, I'm going to use this to maintain a thread lock so that I have safe dictionary access. And why do I need dictionary access? Well, I need my email alert microservice to send me a notification the moment a plane enters the no-fly zone. But as long as it remains in a no-fly zone, do I want an email every 10 milliseconds? I don't think so. We want to throttle those email alerts. So if it remains in the no-fly zone for, let's say, another 30 minutes or whatever we define, then you'll get another email. So we need to track timestamps, which is what this dictionary is, and this is a way of thread safe access to that dictionary, where it's keyed by the flight number, and that's the last time we sent an email, so we don't send an email every 10 milliseconds. The rest of these are needed to be able to send emails. So if you're not familiar with SendGrid, it's a very easy to use service on Azure that lets you send emails, right? Just using a key, and the email is coming from this sender to this recipient. And that's what these privates are above. And this is our spatial business logic that is going to be able to figure out if a plane is entered in a fly zone. So how do we check the flight location? Well, we take the document that comes in. This is a generic document with no defined schema, and we can deserialize it into a class called location event, where you can see it matches the documents in that location container, right? So that I have strongly typed access to it. And it's even actually mapping, camel case to Pascal case for me. So now I've got a strongly typed document, and I'm going to use my spatial business logic to check if it's in a no-fly zone by passing in its latitude and its longitude. This is very basic. You would have a database of no-fly zones, but here I'm just hard coding. The center of Washington, D.C. allowed 150-mile radius, calculate distance, right? And is it within 150 miles? And it is returned as a Boolean, right? If you are in the no-fly zone. Now, if you're not in the no-fly zone, I'll return. I'll just let the event fly by, no pun intended, right? I'm not going to do anything with an event. This microservice isn't doing anything with the events. It's not persisting them anywhere. It's not writing them anywhere. It's just keeping an eye on them in order to know whether it needs to send a notification. And if you're not in a no-fly zone, it just does nothing, and the event just goes by. But now you are in a no-fly zone. I need to send that initial email and then throttle additional emails every minute. So there's a thread lock around the access to that dictionary to keep a thread safe. And I try to see if the dictionary has a last email sent for that flight number. And if it does, if it's less than a minute, I also return and do nothing. Otherwise, the usual logic, if the key is there, if it's not there, we add it. Otherwise, we update it to the current time, and that's it. And obviously send the email. Now, this is something that is a bad practice in the real world of microservices. This is a demo, so it's fine. But we shouldn't be burdening the microservice with actually sending the email, right? The primary purpose of the microservice is to detect if a plane enters a no-fly zone, and if it does, trigger a notification. And by trigger a notification, it should really just write the document to a queue, where another process is picking up on that queue and handling notifications, which could be email, SMS, what have you. You would not want to clutter this microservice up with then support for SMS and other notification methods. You would not want to do that. But it's perfectly, it just increases, I don't care how good of a programmer you are, the more code you have, the more chance there is for an exception to be thrown. There's no question about that. Here, it's very simple. You know, I'm just constructing a nice little HTML email with a table. I've got a method here that formats each table row so the email looks nice. You'll see what the email looks like in a moment. But this actually sends the email, right? But then error checking, did the email go through? You know, was it successfully queued to the SMTP server? Like, you don't want your microservice being concerned with that. All right, and that is the entire microservice. So I'm actually going to kick off my generator now. We're going to watch one flight. And I'm going to kick off my generator in what's called continuous mode, meaning as soon as the plane lands, it's going to take off again. I'll just move the flight map out of the way for a moment so you can see all of the activity start up on all of the other microservices. As soon as the planes start going up, you see there's activity. Right? They're all waking up. They're all getting these events. Every time you see yellow, it means something is happening, right? So what I'm going to do is now show you the flight map. Oh yeah, our plane's in a no-fly zone. You see the flight plane is moving along, moving along. Means I should have gotten an email, right? So let me check my email. Yeah, actually 2 flights have, because I'm only showing 1 flight, but there's another flight that's going, the 2 westbound flights, and they both entered the no-fly zone. So I actually got 2 emails. I'll show you one of them. Here it is. See, look at the date and time. You can see it just happened now, 1:07 p.m. Eastern, and that's a nicely formatted HTML table, right? Showing me that a flight has entered in a fly zone, so I have all the information about the flight, and I'll get more emails if for that flight if it stays in there for more than a minute. Okay, so that's the email alert microservice. I'm going to pause the. I have the ability to pause my planes in midair and just freeze them so that they're just not flying right now. And head on back to the next demo. See if there's any questions to this point.
No questions.
Okay, great. And that is our current location microservice. So we want to get that. We want to query all that telemetry, right? So maybe run a query like so, right? Give me the most recent. So there's a timestamp on each document that's automatically set by Cosmos DB _TS. If you sort by that descending, you're going to get the most recent document. And if you say select top 1, you're going to get the one most recent document for a given flight. And that will certainly enable you to create a flight map that looks like this, right? Like you're seeing. And that's how we're achieving that. So let's take a quick look at that. What I'm going to do is I'm going to resume my planes in the air. And I'm going to show you this we've got one flight, and I'm going to look at the logs, and you can see the queries that are running, because the client is running this query every second. Or every 3 seconds. I'm sorry. You can see every 3 seconds it's running that top one query that I just showed you on the slide, right? And look at the cost, 74 RUs. Now you might not know if that's a lot or not. So let me tell you, that's a lot, and it's just going to be higher the more documents you have in that container, because these are cross-partition queries. Cosmos DB is fanning out to all the partitions for each one of these. It's querying a gargantuan container for what's really it's only mostly interested at any one time at no more than 12 documents. We have 12 planes in the air. We need to know where each one of those 12 planes are, and there's 12 documents that are of interest for this query. And yet we're querying a gargantuan container. And this is actually prohibitively expensive, to be honest, but it works. Yeah, there's the plane. It's going. It works. And you want to make it worse? Let's say all the flights. Now watch these RUs rack up. These request units but look at my map, right? I'm watching 12 flights flying. So I have, in order to watch 12 flights flying, every 3 seconds I'm running this query 12 times. Look at the RUs rack up on the upper left: 53,000, 63,000. 72,000. It's just rising at an alarming rate. This is, again, a bad way to do this. So what I'm going to do instead now is I'm going to click Use Materialized View. Let me turn off all my flights, put only on one flight, and say Use Materialized View. So as soon as the plane lands, it's going to take off because I'm in continuous mode. There we go. So how I got back to New York real quick. And if I look at the logs, look at the cost every 3 seconds. 1 RU. Now, yeah, that's cheap, because I'm now doing a point read from a materialized view, and I'm going to show you the microservice that makes this possible. And so if we flip on it back over to the Azure portal, and I look at the current location microservice, which is when you click that checkbox in the UI, it instead does a point read from this document, from this container. This container has only 12 documents. And to read any one of these documents only costs a single RU, because I'm doing a point read. So if you have a look at the microservice, and that's the current location microservice. Yeah, a lot of the scaffolding is the same. We do have a thread lock with timestamps, right? We can, we can have some throttling for the current location container. It can be up to date within a few seconds. That's fine. And we're monitoring the same container. We're monitoring the same container called location, that big container, and we have a unique prefix on the lease container called current location. And for each document, we're updating the current location, which is really an upsert. We're basically saying what we're doing is we're taking that document, we're calling should skip, which has the throttling logic, and we'll get to that in a moment. But assuming we shouldn't skip it, we take the GUID in the ID, because the ID is just a GUID, which is meaningless, and we replace it with the flight number, right? And then we upsert that item, and we have a maximum of 12 items in that container. And that container is, we'll show you, partitioned on that type property. The type is, of course, location in this case. So anytime you know the partition key and ID of a document, it only costs 1 RU if it's 1K or less. That document in size is 1K or less. It's only going to cost 1 RU. The absolute cheapest operation possible in Cosmos DB. The should skip logic has some throttling. Remember, we never want to miss this one. If it's complete, it means the plane landed. We can't miss that one. So we're always going to return false. But otherwise, we are going to maintain a timestamps dictionary of, for each flight, when's the last time we checked it. And if it's within 3 seconds, we're only going to do this every 3 seconds. We're not going to do it every 10 milliseconds to keep that current location container up to date. And that's the current location container. The only code that I'm going to show you in the front end is that query. If I can find it. Oh, maybe it's in shared flight repo. Yeah, there it is. It's in shared. So that front end, when you are tracking flights, it was calling this query, right? There's the where's the top one? There should be a top one in there. Oh, sorry. Wait a second. What's the top one? Sorry, there it is. Query location. When it queries the location, what it's doing is it's doing that top one query from our location container, which is the very big container. And it is a cross-partition query, and it is very expensive. But when we check that checkbox to do a point read, we are instead reading from the current location, right? That's the target of this microservice where there's only 12 documents. And we just need to do a read. So if we go back to this front end here, and if I go back to the location map and I do 2 flights, well, now it's 2 RUs every 3 seconds, which is not very much. It's going up very small amount. And obviously, if I do 3 flights, now it is 3 RUs every 3 seconds. And you might think if I keep going, that it'll be eventually 12 RUs every 3 seconds if I do all 12 flights. But watch this. I'm going to pick a 4th flight. And now I'm not doing a point read. I'm going back to doing a query. The cost is under 4 RUs because I know my application is smart enough to know that the point of diminishing returns is 4. Once you have 4 flights, it's cheaper to do a single query on that materialized view. This is always a single partition query because we are partitioned on the type property, and they're all in one logical partition, and list in an in clause all the flights that I want, and it costs only 4 U's when I'm asking for 4 flights. And if I bring it all the way up to 12 flights, it's only now under 5 RUs for all 12 flights, not even 12 RUs. Every 3 seconds, it's under 5 RUs. And to just show you again how miserably bad it could be without the materialized view, I'll uncheck this checkbox. We're going back to using the select top one query. And now it's 80, in some cases, 80 RUs times 12 every 3 seconds. Right. So if that doesn't sell you on the value of materialized views, I'm not sure what will. Let me go ahead and shut that off. And we're nearing the end of our presentation because you've hopefully gotten the hang of how these materialized views work, how these microservices work. Here's another example of a materialized view, the arrivals board. Let's get that back on. Just covered that one. I just actually didn't show the slide, but that's exactly what we just did. We just covered this, right? So the arrivals data, it's kind of really similar. If I query that large container in order to figure out, the arrival times of each of the 12 flights, it's going to be very expensive. It's actually quite a bit more complex even than the last example. Instead, we can create a materialized view that will produce documents that look like this. Imagine you have a document that looks like this. It shows you an airport, and then it shows you all of those airports' arrivals. Each arrival and the remaining minutes, so you can easily tell the arrival time. There's Seattle, there's Orlando, right? So what we'll do is we'll have another microservice that creates another materialized view that produces documents like this by watching each document as it flies by. And if I go on over to look at that code, it should look very familiar to you by now. There's our familiar Cosmos DB trigger. There's our familiar thread lock, a timestamp because the arrivals board can be up to date within I think I wrote it to be 5 seconds. Let's see. Yeah, 5 seconds. And I'm not going to go through all of this code because what it's basically doing is it is maintaining a stateful view of the arrivals, and it is just keeping it in. It is just updating it, refreshing it every 10 milliseconds, and then actually writing it to the arrivals container every every 3 seconds. The important parts are here. My try catch. I want to make sure I don't miss my included flight. I want to make sure I don't miss a completed event, and I update the board. And the board is essentially this dictionary, this arrivals board. It's keyed by airport and has airport arrival information, for that airport. And the logic in there is simply to, there's the upsert, right? After checking should skip. You shouldn't skip if the flight landed. Otherwise, you can skip every 5 seconds. And to actually update the board, there's a thread lock around our dictionary that maintains the dictionary. If it's the first time that this airport is being added, or if it needs to update that dictionary with a new flight or an existing flight. So again, not going through all that code, but just maintaining this in-memory representation of the arrivals boards, and then persisting that to our materialized view every 3 seconds. And when that's running, of course, so we can go back to our front end and look at the arrivals board, pick an airport, and those are the planes coming in to JFK. And there are the planes coming into LAX, and going over the logs. The queries for each of these arrivals board queries is just one RU, because they're all point reads, just like the previous example. Our very last microservice is the data archival microservice. I didn't show you this before, but I have this container here called flight history, which was empty when I started. But if I click on it now, this is Azure Blob Storage now. You'll see that it's got a bunch of documents in it. JSON files. These are JSON files. This is not a database. I can just open up any one of them. And have a look at it. Open it up inside of Visual Studio. It looks exactly like a document from Cosmos DB. This is an archived document from Cosmos DB, where the document inside Cosmos DB will expire in 30 days, but it will remain in blob storage forever, or for as long as I need it to, right? So that is our very last microservice. And here's the code for it. Should look super familiar now. You should be able to do this in your sleep by now. Remember, it's just a single function. And you decorate it with the function name attribute, right? And you achieve isolation for the sharing the same lease container with a unique prefix. You name the container that you're modifying. You iterate the documents in a thread-safe way, always catching exceptions. And here, and all I'm doing for each document is archiving the flight location. Again, I'm doing should skip. I don't need to archive every single telemetry document. I want to make sure I don't miss a plane landing. That should not be skipped. But otherwise, every 15 seconds is sufficient for me to capture a document and write it to Azure Blob Storage. So I have a 15-second granularity history of every flight. That's it. That's the whole microservice. Small, simple. That as microservices should be. And I think that's my entire presentation. I mean, there are probably a couple of slides I skipped because I was running late on time, right? This just kind of covers what we did, replicating data to secondary storage, using time to live so that you have a retention within Cosmos DB. And thank you. Thank you very much for attending. I hope you enjoyed the presentation, and I'll pass it on back to you now, Kevin.
All right, we did have one question.
Sure. I'm glad about that.
Can these actually be implemented in Azure? Something like Azure Functions or such?
Yes. So to be clear, I was showing Azure Functions, but I was running them locally. So it might not be obvious, because you see these 4 boxes running on my screen, and you don't realize that, in fact, these are just local. Each of these 4 boxes here is an Azure Function. Each one of them is an Azure function. And just running it locally so I can develop and debug locally. But you can deploy each of these as 4 independent functions, Azure functions, to run in the cloud.
Awesome. That was all of our questions.
Fantastic. Well, then
I'm going to have to go through this presentation at least a couple of times in the code just to make sure I follow along, because
well, again, like I said, I kind of warned you guys at the beginning. It's on the advanced side. I have a couple of other much calmer presentations than that. With that, I'm going to stop sharing my screen and turn it back on over to you, Kev.
Perfect.